Hello and welcome to another episode of Math with Stone. Today we are going to be learning about symmetry and rotations. Let's get into it. So there are several different types of symmetry that we could be encountering. There is something called line symmetry, whereas if you were to draw a line, it could be like folded in like a mirror image and mapped onto itself. You're going to hear that word a lot, mapped onto itself. All right. So line symmetry is where the line would actually be able to reflect it. So the line that I'm drawing right now, if I folded it over on that line, it would be a mirror image of itself, and that would be what we consider line symmetry. Point symmetry is the next one, and this one's kind of weird. If point symmetry means that if you were to rotate the image 180 degrees, it would be mapped onto itself. So if I flip this paper upside down, notice how n still is n. That means that I rotated it 180, but it's still the exact same thing I was looking at before. Therefore, it would have point symmetry. If it has point symmetry, it definitely has rotational symmetry. So rotational symmetry is meaning that you can rotate this any amount of times and it would be mapped onto itself. So this sun that we have here, I could rotate it quite a few times and it would be the exact same image over and over again, and the exact amount of times that is matters. Okay, so rotational symmetry oftentimes is involving something that they say is how many degrees would you have to rotate it in order for it to be mapped onto itself. So what you could do is you could count up 1, 2, 3, 4, 5, 6, 7, 8. There are 8 rays on this sunshine, and if you take the number 360 and divide by 8, that would tell you how many degrees you would have to rotate in order for it to be mapped onto itself. And 360 divided by 8 is, boy, it has been a long day. 360 divided by 8 is definitely not 60 degrees. It is 45. Big boo-boo. I had to run and get a calculator. So every 45 degrees that we rotate, it would be the same exact image as before. So we're going to do a few practice problems, and then we're going to be done. So we got a hexagon here. Hexagon has 1, 2, 3, 4, 5, 6 sides. And the amount of sides oftentimes is a clue as to how many lines of symmetry it may or may not have. This, of course, definitely has point symmetry. We're going to check that box right now. So it definitely has point symmetry, and that is because we could flip it upside down and get the exact same thing. The line symmetry that it has definitely has line symmetry. It has 1, 2, 3 lines of symmetry here. But you remember how I said it had 6 sides? It should have 6 lines of symmetry. And the 6 lines of symmetry is actually going to be when we go from corner to corner. 4, 5, 6, when we go from corner to corner on the shape. So it has 6 lines of symmetry. It definitely could be turned upside down. And normally when you're dealing with a regular shape like this, a regular is like normal shape, the amount of line symmetry is also how many times you can rotate it and end up with the exact same shape. You can notice that we end up with the exact same shape numerous times here, and it definitely has rotational symmetry. If you were to divide 360 by the 6, it would actually be 60 degrees in order for it to be mapped onto itself. And that is something that is important. Now we got a triangle for number 2. This triangle definitely has some line symmetry. You could cut it right in half that away, and this away, and straight down the middle. It does not have point symmetry, though, because if you turn this upside down, you have a triangle that is literally a point. And that is not what we were looking at before. It has to be the exact same thing. Where here we have a flat bottom. When we rotate it upside down, we got a point at the bottom. So, not going to have point symmetry. But that doesn't mean it doesn't have rotational symmetry, because instead of turning it all the way 180 upside down, if we just turn it once, we could have this bottom part be here, and again we could have that bottom part be here. So it does have 3 rotations of symmetry, and if you divided 360 by 3, you would get the 120 degrees before it would be mapped onto itself. Next one, number 3. So this one, it looks like it has some line symmetry. It really does. But it absolutely just does not. Okay, if you were to take this, and I'm going to draw another one, just so I can prove it. So if we were to take this, and we were to draw a line here, this point reflected over would end up over here, not where it actually is. And this point would end up inside it. That's not where it is either. Now, some people may say, well, what if you do this way? Well, if you do it that way, these 2 points obviously are, but these points would actually end up over here and over here as well, so they're not going to end up mapping onto itself. Like if you folded it, if you actually took the paper and folded it, you would see these really just don't line up perfectly, which is kind of a shame because it really looked like it would. It also may or may not have point symmetry, so we're going to be careful. When I'm going to rotate this, right now, the bottom left is really far to the bottom left, and the top right is very far to the top right. So I'm going to rotate it and see if that actually stays the same. So far, bottom left is in the bottom left, like all the way to the bottom left. So if I turn it upside down, is that still the case? Yes. This bottom left part is still in the far bottom left part, and the top right is still in the very far top right part. So when we do flip it over 180, it worked. And that would also mean that rotational symmetry would work as well. And it only has that one rotational symmetry, so this would actually be 360 divided by 2 is 180. It only has that one. When you flip it upside down, that's the only time it works. Looking at number 4, this one has no symmetry at all. You can't draw a line here and cut it in half. That's not a perfect mirror image. You also can't turn that upside down. If you turn it upside down, it won't work. Nor rotate it. It has no symmetry. There is nothing happening here that is symmetrical, and we would click none. I clicked it so many times I had to circle it. 5, it's a star. Obviously, it's got some symmetry. It's got tons of lines of symmetry. It has maybe point symmetry. We got to be careful with that. Like here, we're looking at like it has the 2 legs, but if I flip it upside down, its head, like if you think of a star as like a human, its head would be facing the ground. So right now we have 2 points, but as soon as I flip it upside down, there's a single point on the bottom, not 2. So it does not have point symmetry, but it definitely has some rotational symmetry. Like you could turn this thing a lot of different times and end up with 2 legs at the bottom. I could just turn it slightly less and I have 2 legs at the bottom. So there's definitely rotational symmetry, and that is according to how many points it has. 1, 2, 3, 4, 5 points. Whatever 360 divided by 5 is would tell you how many degrees you would have to rotate. Number 6, does it have line symmetry? I don't think so. I really don't think so. I think if we flip it over this diagonal line, it won't work. If we flip it over this vertical line, it won't work because this part would end up on the top again. So I don't think it has line symmetry, guys. It does look like it might have point symmetry, though. If we turn this from the center 180, does it end up being the same thing? So here I'm looking at bottom left and the bottom left and top right and the top right. And when I flip it back over, bottom left was in the bottom left and top right was in the top right. So this does have point symmetry. And if it has point symmetry, it has rotational symmetry. It looks like it's only going to be that one time when you flip it over. The letter A has a single line of symmetry. And there is no way you can rotate this shape and make it look like an A again. If you turn it upside down, it looks more like a V. So that's not going to have any sort of rotational symmetry at all, which means it doesn't have point symmetry, and it doesn't have anything except that one line of symmetry. This lightning bolt has nothing that I can see. If we turn it upside down, yes, it looks like a lightning bolt, but like it changes. It's not the same image that we were looking at before. Now the point is in the top right corner. Before it was in the bottom left-hand corner. So it's not in the same exact location. Therefore, we cannot say that this has true point symmetry or rotational symmetry. And I don't think that you can draw a line anywhere where you can map it onto itself. So this one just has none. All right, that's going to do it for today's episode, everybody. Have a good one, and I will see everybody later.